These are your notes for Unit 3, Day 2 of Calculus. If you would like to see your warm-up, review question, or any homework questions we went over in class today, just look at your finished notes. So today we are going to continue talking about the first derivative and also the second derivative, and how using those two functions allow us to talk about the graph of the original function. The first derivative allows us to talk about when the original function is increasing or decreasing. It also allows us to find the minimums and maximums, the relative extrema on the function. The second derivative, this will be new today, we'll talk about how it allows us to talk about the concavity on a graph, so where the graph is concave up or concave down, and where the graph, the original graph, changes concavity, which we call a point of inflection. So the first derivatives test for finding relative mins and relative maxes, we talked about this last class. So for a function to have a relative min or a relative max, you have steps to follow. Your first step is you need to find the critical numbers. And remember from last class, the critical numbers are when the first derivative is equal to 0 or where the first derivative is undefined. So when the first derivative is equal to 0, you could have like a function that looks like this. And where it's equal to 0, it has a peak or a valley. So obviously that would have a relative min or a relative max when the slope of its tangent line is 0. It could also have a relative min or a relative max where the derivative is undefined, because it could look like an absolute value graph. And notice at the top of that absolute value graph, the slope is undefined because one slope's positive and one slope's negative. So there, this derivative would be undefined. Or at a cusp, so where a line meets a curve, it could have a relative minimum or a relative maximum as well. And the derivative would be undefined at a cusp. So your first step to find the relative extrema of a function is you have to find the critical number. So you want to find where the derivative is equal to 0 or where the derivative is undefined. After that, you have to make a sign chart with the critical numbers. So you make a sign chart with your critical numbers to figure out where the derivative changes signs. So when f prime of x is equal to 0, and it changes from positive values to negative values. So the derivative was positive, so the slopes of your tangent lines were positive, and then at the top they were 0, and then afterwards the slopes of the tangent lines are negative. So the derivative changes from positive values to negative values. That represents a relative maximum. So when the derivative is equal to 0 and before it was positive and after it was negative, that represents a relative maximum. And then if the derivative is 0 or undefined, I should say. So if the derivatives are 0 or undefined, and then the derivative was negative, but then after the 0 it was positive, then that represents a relative or local minimum. And that's how you use the first derivatives test to find relative mins and maxes on a function. So for instance, we can just look at a parabola really quick. So if f of x equals x squared minus 2x plus 4, and we want to find the relative extrema on that function, first you would figure out where the derivative is equal to 0. So the derivative is 2x minus 2. Set that equal to 0 and solve, and you would get x equals 1. So that would be my critical number. And now you put that in a sign chart. So we know that the derivative is 0 at 1. So this is the x value, this is the derivative value. And then you test numbers before and after that. So I could test 0 and 10. And if you plug those into the derivative, if I plug 0 into the derivative, I get negative values. And if I plug 10 into the derivative, I get positive values. So the derivative goes from negative values to positive values. So the function was decreasing, then it's increasing. So at x equals 1, you have a local minimum. And if you want to find the actual height of the local minimum, you take the x value and you plug it back into the original. So f at 1 is going to equal 1 squared minus 2 times 1 plus 4. So this would be 1 minus 2 plus 4, which is 3. So at the point 1, 3, my function, the original function, x squared minus 2x plus 4, has a local minimum. All right. Intervals of increasing and decreasing. So a function is increasing and decreasing if it's polynomial, or any function really can be. So it's increasing when the graph is climbing, and it's decreasing when the graph is falling. And then it changes when it's at a peak or a valley. So to figure out where a graph is increasing or decreasing, you look at the slopes of the tangent lines. When the derivative is positive, that means that the slope of the tangent lines are positive. So f of x would be increasing. So if f prime of x is greater than 0, or if the derivative is positive, then f of x is increasing. And then where f prime of x is less than 0, so where the slopes of the tangent lines are negative, then the original function would be decreasing. So to look for increasing and decreasing, you look for where the first derivative is positive or negative. So a function is increasing if f prime of x is greater than 0. So let's look at that function again. X squared equals x squared minus 2x, and then I think it was plus 4. So if we want to figure out where this function is increasing, you take the derivative, 2x minus 2, you set it equal to 0, and then we get x equals 1. So again, your steps, you need to find the critical numbers, and then you do the sign chart. And in the sign chart, you're trying to figure out where the derivative is positive. So we know the derivative is 0 when it's 1. And then we will look to the left and to the right of it. So I could look at 0 and I could look at 10. And if I plug in 0 and 10, I would get negative and positive. So the function is increasing where the derivative is positive, and the derivative is positive as long as you are greater than 1. So my function, f of x, is increasing when x is greater than 1, or you can write it in interval notation from 1 to infinity. A function is decreasing if the derivative is negative. So if f prime of x is less than 0, then the function is decreasing. So again, you find your critical numbers, and then you find your sign chart. And if you want to figure out where the function is decreasing, you're looking for where f prime of x is less than 0. So you're looking for where f prime of x is negative. So if we have f of x equals x squared minus 2x plus 4, then its derivative would be 2x minus 2. And so the derivative is going to be 0 at 1. That's my critical number. And then again, we make the same sign chart. So we know that the derivative is 0 at 1. And then we're going to do tests. So we can test 0, we can test 10. And we've already done this. It's negative to the left of 1, and it's positive to the right of 1. And so f of x is decreasing when x is smaller than 1. That's where my negative is. So if x is less than 1, my function is decreasing. So from negative infinity to 1, the function is decreasing. So let's look at some more examples. So to determine where the function is increasing and decreasing. So we need to figure out where the derivative is 0 or undefined. So we'll find the derivative first. So the derivative would be negative 2x plus 8. Set that equal to 0. And subtract the 8 and divide by negative 2. And you get a critical number of 4. So we know that the derivative is 0 at 4. And then we've got to test before and after that. So we'll test 0 and 10. And if I take 0 and plug it into the derivative, and again, the derivative was negative 2x plus 8. If I plug 0 in, I get positive. If I plug 10 in, I get negative. So f of x is increasing from negative infinity to 4. So when x is less than 4, the function is increasing. And f of x is decreasing on the interval from 4 to infinity. So if x is greater than 4, the function is decreasing. On the second one, we're going to have to use quotient rule. So derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. And so when you want to test where the derivative is 0 or undefined, well, this is a fraction, so let's simplify the numerator a little bit. We're going to have negative 2x squared minus 14x, and then plus x squared, and then minus 36 all over x plus 7 squared. Again, I'm going to simplify it one more time, and I'm going to get negative x squared minus 14x minus 36 all over x plus 7 squared. So the derivative is going to equal 0. I'm going to add a page just in case I'm going to run out of room. The derivative equals 0. So f prime of x is going to equal 0 when the numerator is equal to 0. And f prime of x is going to be undefined when the denominator is 0. So when your derivative is a fraction, you set the numerator equal to 0 and the denominator equal to 0 to find your critical numbers. So we want to know when negative x squared minus 14x minus 36 is equal to 0. Well, I can factor out a negative 1, and I would get x squared plus 14x plus 36 equals 0. So can we multiply to 36 and add to 14? 9 and 4, nope. So this would have to be the quadratic formula if it has any answers. So x would equal the opposite of b plus or minus the square root of b squared minus 4 times a times c. So that would be 14 squared minus 4 times a times c, all over 2 times a. And so x would equal 14 plus or minus the square root of 196, and then minus 144, all over negative 2. And so that is going to give me some answers. And then when is the denominator 0? X plus 7 squared equals 0. So this would be when x equals negative 7. So we know negative 7 is going to go. And then let's go on Desmos and figure out for my calculator where this guy would equal 0. So we want to know when negative x squared minus 14x, minus 14x and minus 36, where that's equal to 0. So it's going to equal 0. And I'm just going to use Desmos decimals, so negative 10.606 and negative 3.394. So my critical numbers are going to be those three numbers. So we'll make a sign chart. Negative 10.606, negative 7, and then negative 3.394. And that's where my derivative is 0 or undefined. It's 0 at, it's undefined at negative 7, and it's 0 at the other two places. And then we're going to test. So I could test negative 20, I could test negative 8, I could test negative 5, and I could test 0. And we're going to plug it into the derivative function. And so my derivative function is negative x squared minus 14x minus 36 all over x plus 7 squared. Well, since the denominator is squared, it's always going to be positive, so I just have to plug into the numerator. If I plug 0 in, I get negatives. If I plug negative 5 in, I would get negatives. If I plug negative 8 in, I would get negative 64. Let's just make sure we don't make any little math mistakes. So let's pull up Desmos. So if I plug in negative 20, that would be negative 20 squared, and then minus 14 times negative 20, and then minus 36. So that's going to be negative. So if I plug in negative 20, it's negative. If I plug in negative 8, that would be times negative 8. That would be positive. And if I plug in negative 5, and then negative 5, that would be positive. And then if I plugged in 0, we got negative. So that looks better. All right. So where is this function increasing and decreasing? Well, it's decreasing when the derivative is negative. And so it's decreasing from negative infinity to negative 10.606. And it is decreasing from negative 3.94 to infinity. And where is it increasing? It's increasing where it's positive, so from negative 10.606 to negative 7, and from negative 7 to negative 3.394. So that's where the function is increasing and decreasing. All right. So find any critical numbers and then use the derivative test to find any local mins or local maxes, and then state where the function is increasing or decreasing. So critical numbers first, that would be when the derivative is 0 or undefined. So 4x cubed minus 4x equals 0. We can factor out a 4x, and we would have x squared minus 1. So x is either equal to 0 or plus or minus 1. So we'll make a sign chart, negative 1, 0, and 1. So that's where my derivative is 0. So those are my critical numbers. And so we could test negative 10, negative 0.5, positive 0.5, and positive 10. And if I plug those into the derivative, which was 4x times x squared minus 1, if I plug in negative 10, I would have a negative times a positive, so negative. If I plug in negative 0.5, I'd have a negative times a negative, so a positive. If I plug in 0.5, I'd have a positive times a negative, so a negative. And if I plugged in 10, I'd get a positive. So for local mins and local maxes, well, the derivative has to equal 0 and change signs. On the first one, my derivative was negative, and then it was positive. So at x equals negative 1, we have a local minimum. At 0, the derivative changes from positive to negative. So at x equals 0, you have a local or relative maximum. And then at positive 1, the derivative changes from negative to positive. So that would be a local minimum. And then where is the function increasing and decreasing? Well, where is the derivative positive and negative? So the derivative, where the derivative is positive, my function is increasing. So it's increasing between negative 1 and 0, and then from 1 to infinity. And then my function is decreasing when the derivative is negative. So it is decreasing from negative infinity to negative 1, and from 0 to 1. All right, you guys can go ahead and try the second one, f of x equals x to the third plus x squared minus x. Go ahead and figure out where that function has local mins and local maxes and where it's increasing and decreasing. And you can check your work against the finish notes. All right, let's go ahead and do another one. So let's look at that first one. So the derivative would be 12x to the third minus 12x squared minus 72x. And we want to know where this is equal to 0. So I'm going to factor out a 12x, and I would get x squared minus x minus 6 equals 0. So this would be 12x, and that would factor into x minus 3x plus 2. So my critical numbers, where the derivative is equal to 0, would be 0, 3, and negative 2. And we can make a sign chart, negative 2, 0, and 3. And then that's where my derivative is equal to 0. And then we test to the left, so I could test negative 10. Negative 1 is in between, positive 1 is in between, and then positive 10. And then I can plug into the derivative 12x times x minus 3 times x plus 2. If I plug in negative 10, I have 3 negatives, so it'd be negative. If I plug in negative 1, I'd get 2 negatives and a positive, so that'd be a positive. If I plug in 1, I'd get 2 positives and a negative, so negative. If I plugged in 10, all would be positive. So my derivative changes from negative to positive at x equals negative 2, so that would be a local minimum or a relative minimum. And then it changes from positive to negative at 0, so at x equals 0, I'd have a local maximum. And then it changes from negative to positive at x equals 3, so I'd have a local minimum again. And then my function is increasing where the derivative is positive, and the derivative is positive between negative 2 and 0, and then 3 to infinity. And then my function is decreasing where the derivative is negative, so from negative infinity to negative 2, and between 0 and 3. On the second one, go ahead and try that, and again, check it against the finish notes. All right, so concavity. What is concavity? So you might remember when we graphed parabolas, a happy parabola, a parabola that opens up, we call concave up. So wherever a graph looks like that, we call it concave up. And if it was negative x squared, the parabola opens down, and we call that concave down. So on a graph, on a polynomial function, it could have several of those peaks and valleys. So if my function looks like this, my function would be concave up to about right there. So this, or sorry, it would be concave down. So this would represent a function that's concave down. And then my function changes concavity at that point right there. And then afterwards, we would call that part of the function concave up. The place where it changes concavity, that point right there, it's the change in concavity. So it changes from concave down to concave up. We call that an inflection point, or a point of inflection. In order to talk about concavity, or to find concavity on our original function, we look at the second derivative. So concavity and the second derivative. So if you want a function, or if you want to figure out where a function is concave up, a function is going to be concave up when its second derivative is greater than 0. So you need the second derivative to be positive for a function to be concave up. And a function is going to be concave down when the second derivative is negative. So if you want to figure out where a function is concave up or concave down, you look for the second derivative. So for instance, if I had f of x equals 1/3 x cubed minus 1/2 x squared minus 6x, and we wanted to figure out where this function is concave up and concave down, your first step you would take the first derivative. So my first derivative would be x squared, and then my minus x minus 6, and then you would take its second derivative, and its second derivative is 2x minus 1. And then you would figure out where this is equal to 0, because we need to make a sign chart. So my second derivative is equal to 0 when x is 1/2. Now we need to figure out whether the second derivative is positive or negative, so we make a sign chart. So at 1/2, the second derivative is 0. And then we test before and after. So we can test 0 and we could test 3. And you plug it into the second derivative. So if I plug in 0, the second derivative is negative. And if I plug in 3, the second derivative is positive. So the second derivative tells you about concavity. So the original function is going to be concave up when the second derivative is positive. And that's going to be from 1/2 to infinity, or if x is greater than 1/2, because this is where my second derivative is positive. And then the original function is going to be concave down when x is less than 1/2, so from negative infinity to 1/2. So if I were to go on Desmos and graph that function, so the original function was 1/3 x to the third minus 1/2 x squared minus 6x. So that's my original function, and it changes concavity somewhere in here, which we said 1/2. So at about 1/2, x equals 1/2, it looks like it changes concavity. And if you notice on the graph, it does. It looks like it changes concavity at about 1/2. It changes from concave down to concave up. All right. So how do you find the point of inflection? So a point of inflection, again, is where the graph changes concavity. So where f of x, the original function, so where f of x changes concavity. That's a point of inflection. And how you find it is where the second derivative equals 0 or is undefined, just like critical numbers. So you find where the second derivative is equal to 0 and is undefined, and it has to change sign. So it has to change concavity. It has to go from concave up to concave down, or concave down to concave up. So it has to change signs. So to test for a point of inflection, you have to figure out where the second derivative is 0 and changes sign. So if we go back up to our previous problem, the second derivative is equal to 0 at 1/2, and it changed signs because it went from negative to positive. So when x equals 1/2, you have a point of inflection because the second derivative was equal to 0 and it changed signs. So let's go ahead and find the intervals of concavity and any points of inflection on these graphs. So we have to find the second derivative. So first find the first derivative. So this would be 4x to the third minus 4x is the first derivative. The second derivative is going to be 12x squared minus 4. We want to know when that's equal to 0. So we have 12x squared equals 4, x squared equals 1/3. So x is going to equal plus or minus the square root of 1/3. All right, let's go ahead and make a sign chart. So negative square root 1/3, positive square root 1/3. We got to test numbers to the left, in the middle, and to the right. So I'm going to test negative 10, 0, and positive 10. And I'm going to plug them into the second derivative, which was 12x squared minus 4. If I plug in negative 10, I get positive. If I plug in, at negative and positive square root 1/3, those are zeros for the second derivative. If I plug in 0, I get negative. And if I plug in positive 10, I get positives. So my graph, the original f of x function, is going to be concave up from negative infinity to negative square root 1/3, because that's where the second derivative is positive, and also from positive square root 1/3 to infinity. And then my original function is going to be concave down, where the second derivative is negative, so from negative square root 1/3 to positive square root 1/3. And where does the function have a point of inflection? Well, the original function is going to have a point of inflection where the second derivative is equal to 0 and changes signs, and that occurs when x equals plus or minus the square root of 1/3. All right, let's go ahead and look at the second one. So find the first derivative. The first derivative is 3x squared plus 2x minus 1. Then find the second derivative. The second derivative is 6x plus 2. And we want to know where that's equal to 0. Well, that's going to equal 0 at negative 1/3. Make a sign chart. That'd be 0. And then we can test before and after. So negative 10 and 0. If I plug negative 10 into the second derivative, I get negative. If I plug in 0, I get positive. So this function is going to be concave up when its second derivative is positive, so from negative 1/3 to infinity. And it's going to be concave down where the second derivative is negative, so from negative infinity to negative 1/3. And it has a point of inflection, and I'm just going to abbreviate that POI at x equals negative 1/3, because that's where the second derivative is equal to 0 and changes signs. All right, let's do one more. Let's do f of x equals x plus 4 over x. So this is going to be x plus 4x to the negative 1. So to find points of inflection, we got to figure out where the second derivative is equal to 0 or is undefined. So the first derivative is 1, then minus 4x to the negative 2. And then the second derivative is going to be 8x to the negative 3, or 8 over x to the third. Since it's a fraction is going to equal 0 at when the numerator is equal to 0. The numerator is never going to equal 0 because it's 8, or it's undefined when the denominator is 0. Well, the denominator is going to equal 0 when x to the third equals 0, so that's when x equals 0. So my second derivative is undefined when x is equal to 0. So that's going to be a critical number for points of inflection if you want to think about it that way. So now we're going to test before and after that. So we'll test at negative 1 and positive 1. If I plug negative 1 into the second derivative, I get negative. If I plug positive 1s in, I get positive. So my original function is going to be concave down when the second derivative is negative, so from negative infinity to 0. And then it's going to be concave up when the second derivative is positive, so from 0 to infinity. And this has a point of inflection at x equals 0, because that's when the second derivative is undefined and changes signs. So you guys can go ahead and try that fourth one, and you can check your answer against the finish notes. All right, let's read some graphs. So this is a picture of f prime. So this is a picture of the first derivative. On what intervals is the original function? So f is the original function. When would the original function be increasing? Well, the original function is increasing when the derivative is positive. So where on this graph is f prime positive? Well, it's positive when it's above the x-axis. So it would be positive from negative infinity to negative 2, and then at negative 2 it's 0, so it's not positive. And then it's also positive from negative 2 to 1, because it's above the x-axis. So that's when the original function would be increasing. All right. When is the original function concave up? Well, the original function is going to be concave up when the second derivative is positive. What's the relationship between the first derivative and the second derivative? Well, f double prime are going to be the slopes of this graph. So where are the slopes of this graph positive? Where are the slopes of the tangent line positive? Well, they'd be positive here, because that's where the function is increasing. So where is the original function concave up? It would be when f double prime of x is greater than 0, or when the slopes of this graph are greater than 0, so when this function is increasing. So from negative 2 to infinity, and also right here. So it looks like from 3 to 4. That's when the graph of the original function would be concave up. All right. the next part says, when would the f function have local extrema? Well, it would have local extrema when the derivative is equal to 0 and changes signs. So where is the derivative equal to 0? Well, the derivative is equal to 0 at -2, 1, and 4. But the derivative also has to change signs for it to be a local extrema. Well, here the derivative is positive, and here the derivative is positive. So at -2, the derivative didn't change signs, so that is not going to be a local extrema. We call that a plateau point. At 1, the derivative changes from positive values to negative values, so we do have a local extrema at x equals 1. At x equals 4, the derivative is equal to 0, but we don't know if there's a change in sign because we don't know what's happening afterwards. All right, for D, at what are the x coordinates where you have points of inflection? Well, we have points of inflection when the second derivative is equal to 0 and changes signs. Well, the second derivative is going to be the slopes on this picture. So we need the slope of this picture to be 0. Where are the slopes 0? Well, there's zeros at the peaks and the valleys. So the second derivative is going to be 0 at -2, 0, and 3. Did the second derivative change signs at those? Well, it's going to be the slopes. So here the slope is negative. Here the slope is positive. So at x equals -2, the slopes change signs. So we have a point of inflection at x equals -2. And then at 0, the slopes of my function went from positive to negative. So again, they change signs. So at x equals 1, we also have a point of inflection because the second derivative would be 0 and changes signs. And then same thing at 3. So you have points of inflection at -2, 1, and 3. Sketch a possible graph of f between -4 and 4. Okay, so if we want to sketch a possible graph using that information, well, we know that our function is increasing between -infinity and -2. So here's -2. So we know it's climbing between -infinity and -2 and between -2 and +1. So it's climbing that whole time. But at -2, we know it's going to hit a plateau point because the derivative went from positive to positive. So if we drew this, we could draw it, and then it kind of plateaus out, and then it continues increasing to 1. And then at 1, notice the derivative was 0 and it changed from positive to negative. So if your derivative is 0 and it changes from positive values to negative values, you have a maximum. So we have a maximum value at 1. And then my function is going to start decreasing afterwards. And then when is the graph concave up? The graph is concave up from -2 to 0. And it looks like I kind of make it look concave up right there. So that looks good. And points of inflection happen at -2, so that looks good. It looks like it changed concavity. At 1, it looks like it's changing concavity at 1, and then also at 3, it needs to change concavity. So at 3, it needs to change concavity. Well, change concavity. And there we go. That could be a possible graph. We can also use the second derivative to determine whether a function has a relative min or a relative max at a given point. So how would we do that? So if this is my original function, we know that it has a relative maximum right here. Well, what happens to have a relative maximum? We know from the first derivative test that the derivative would have to equal, the first derivative would have to equal 0 or be undefined, and it has to change from positive values to negative values. Or we can know when the first derivative is 0, what's true about the second derivative at a maximum? What type of concavity exists right there? It's concave down. So if you're concave down, the second derivative is going to be less than 0. So if you know that the first derivative is equal to 0 and the second derivative is less than 0, then you're going to have a maximum, a local maximum at that point. Or we know that the first derivative is equal to 0 there. And so if the first derivative is equal to 0, and then what do you know about the concavity there? Well, this graph is concave up right there. So if your first derivative is equal to 0 and the graph is concave up, so the second derivative is positive, then you would have a local minimum at that point. And that's called the second derivatives test. So instead of making a sign chart to figure out whether you have a local minimum or a local maximum, if it's easy to find the second derivative, you can use the second derivative to determine whether or not that point is a minimum or a maximum. So for example, we can use the second derivatives test here if we wanted to. So first we need to find the critical number. So f prime of x is equal to 0 undefined. So this is 3x squared plus 12x minus 36. I'm going to factor out a 3, and I get x squared plus 4x minus 12 equals 0. And then this would factor into x plus 6, x plus 2, or sorry, x plus 6x minus 2. And so my critical numbers are negative 6 and positive 2. And instead of having to make a sign chart, I'm going to figure out what's happening to the second derivative at both negative 6 and positive 2. So my second derivative is going to be 6x plus 12. So if I take my critical numbers and plug them into the second derivative, so if I plug in negative 6, I get 6 times negative 6 plus 12, which is going to be negative 36 plus 12, which is negative 24. So at x equals negative 6, we know that the first derivative is 0, and we know that the second derivative is less than 0, so it's concave down. Well, if that's true, then you have a local maximum when x is equal to negative 6. If I take the other critical number 2 and plug it in, then I get 6 times 2 plus 12, which is positive 24. So at x equals 2, we know that the first derivative was 0, and we know the second derivative is positive. So if it's positive, that means that the graph is concave up. So this would be a local minimum. So at x equals 2, you have a local minimum. And that's the second derivatives test. So go ahead and use your second derivatives test to try and figure out where this graph would have local minimums and local maximums. You guys can pause the video, try, and then you can check your work against the finish notes from class today. All right, we are going to sketch f from f prime. So let f prime of x be 4x to the third minus 12x squared. Identify where extrema occur. Well, extrema occur when the derivative is equal to 0. So we're going to factor out a 4x squared, and then we would have x minus 3. So I have extrema, I have critical numbers at 0 and 3. So make a sign chart, x equals 0, x equals 3. So I know my derivative is 0 at those two places. I'm going to test negative 1, 1, and 10. If I plug negative 1 in, I get negatives. If I plug positive 1 in, I get negatives. And if I plug 10 in, I get positives. So at 0, we're going to have a plateau point. And then at 3, the derivative changes from negatives to positives. So that's going to represent a local minimum. Find the intervals when the function is increasing or decreasing. The original function is increasing when the first derivative is positive, so from 3 to infinity. And then the original function is going to be decreasing when the derivative is negative, so from negative infinity to 0, and from 0 to 3, my original function will be decreasing. Concavity, we need to look at the second derivative. So my second derivative is going to be the derivative of the first. So 12x squared minus 24x. Set that equal to 0. I'm going to pull out a 12x, and then I would have x minus 2. So my points of inflection could occur at 0 and 2, but we got to make a sign chart and make sure that it changes signs at both of those places. So 0, 0. I'm going to test negative 1, 1, and 10. If I plug negative 1 in, I get a positive. If I plug positive 1 in, I get a negative. And if I plug 10 in, I get a positive. So the original function is going to be concave up when the second derivative is positive. So from negative infinity to 0 and from 2 to infinity. And the original function is going to be concave down from 0 to 2. And then the original function has a point of inflection at x equals 0 and at x equals 2, because that's where the second derivative is equal to 0 and changes signs. Go ahead and see if you guys can use that information to sketch a picture of the original function, and you guys can check your sketch against our finished notes from class today. Some review of position, velocity, and acceleration. So remember, if you're given a position function, you can find the velocity function by taking the derivative of that. So 6t squared minus 28t plus 22. And you can find the acceleration function by finding the derivative of velocity, so 12t minus 28. And then you can use the exact same steps that we did up above to sketch a picture of the displacement graph using that information.